This is a derivation of the force of interaction between two wires that are carrying currents in the opposite direction. The force law we're going to be using is this one. Instead of Q times V cross B, remember this is the force law that we use for discrete charges that we're moving relative to a magnetic field. If we have a stream of charges, what we call a current, then it takes on this form. Again, B is your magnetic field. L is the length of the wire segment. L is a vector, so it points in the same direction as a current. Remember, current's a scalar, but we'll treat it similar to a vector. So what I have here are two lengths of wire. They're the same length. They're parallel to each other. They're separated by a distance d. And I've got a current flowing this way that I'll call I1, and I've got a current flowing this way that I'll call I2. I1 produces a magnetic field down here, which this current will interact with. This current produces magnetic field up here that this current will interact with. So there'll be two forces of interaction. We'll show that if the currents are moving in or flowing in opposite directions, then the force of interaction is repulsive. If this wire happens to be stationary and this one is movable, then the force of repulsion will push this one up. And so any weight that you put on here will tend to counteract it. Okay, so let's just try it. So by the right-hand rule, if I take the thumb of my right hand along I1, then my fingers will wrap around to form the B field. So the B field will wrap around this way. So as the B field comes down here, it will be pointing into the board. And I'll call that B1. That'll be the magnetic field produced by current I1. This current right here, again, if I take the thumb of my right hand along I2, my fingers wrap this way, so up here, this current will interact with a magnetic field that's pointing into the board, and I'll call that B2 caused by I2. Okay, so that gives us all the vectors that we need. Now the only other thing we need to do before we work out the equation is to use the right-hand rule to figure out the direction of the force. So I1 will interact with B2. So if I take I1 and wrap it into B2, my thumb points up. So if you have trouble seeing that, you use these markers. This marker will represent I1. This marker will represent B2. So they will form a right angle like this. So B2 is pointing into the page. So if I take I1 wrapped into B2, I'll be wrapping my fingers this way. I'll be wrapping the vector like this. My thumb will point up. So we'll call that force F1. Down here, I have I2 pointing this way, B1 pointing this way. So again, if I use this as my current vector, I2, B1 will be pointing in. If I take the fingers of my right hand and wrap it this way into B1, my thumb points down. So that'll be F2. So the right-hand rule in this form shows that the force of interaction, if you have two parallel but opposite currents, is repulsive. Okay, so let's work it out. The way your experiment's going to work is the lengths of wire will be the same, and the apparatus is designed so that the current values here and here are the same. So I can get rid of the subscripts here. If this current's the same as this current, then this magnetic field has the same magnitude as this magnetic field, so I can get rid of those subscripts. That means I can get rid of these subscripts. So now all I have to do is work out what F is. All the angles involved are 90 degrees, so there's no sine or cosine that shows up. So I have ILV is my force of interaction on either wire. Leave the leave the IL alone and put in what the B field is. Well, you should remember that the magnetic field produced by a long, thin, current-carrying wire is just equal to this. This D is how far away the field point is from the source of the field, so that'll be the separation distance D here. Okay, again, these currents are the same, so I can group them together. So I get mu0 L over 2 pi d times I squared. Okay. Now the goal of the experiment is this wire is stationary, this wire is movable. So what you'll do is you'll measure distance d, that'll be your equilibrium position, and then you'll simply put a small mass on here. That'll cause this wire to move down slightly to get closer to this stationary wire, and then you'll put current through the system to allow this force to push the wire back up until you reach equilibrium position D again. And so how much current you have to put in is directly related to how much mass that you have there. So, since I'm looking for equilibrium, I'll just set that force equal to the mass times g, or the weight that I put on that little portion. So what you'll do is you'll take a set of data that'll be mass and current. Current will be measured in amps. These masses tend to be pretty small, so they're measured in milligrams. So the one thing you would have to do is, you'll see in the data set that I went from about 5 milligrams up to I think 60 milligrams. Well, there's 1,000 milligrams in a gram and 1,000 grams in a kilogram. So you're going to have to take those masses and divide by 1 million and then multiply by g to get the weight. So you'll have about 7 or 8 values here. And then all you have to do is make a plot. If you plot mg on the vertical axis and I squared on the horizontal axis, you should get a nice straight line. You fit the data to a straight line, and then the slope will just equal this quantity in the brackets. So you'll have mu 0L over 2 pi d. And that's it. So from the slope you can figure out a numerical value for mu 0 and then compare it to the known value. For this experiment, I measured L to be 30 centimeters or 0.3 meters for the movable wire. And then the distance d that I had for equilibrium before I put any mass on was 3.75 millimeters, so 0.00375 meters. Okay, then all you have to do is take the data that I gave you, make the plot, figure out the slope, use the values for L and D, and then compute mu 0.